Here we go. Hopefully you can see this. Uh, and I know you can. I'm looking at the same presentation on my phone. So check valves are what? Again, I'm Mark Hall and I'm Area Specification Manager for the Bay Area and Sacramento. So swing check valve. There's the two check valves that we're going to talk about today are swing and spring, just for starters. So you can see on this graphic, this is the inside of this particular check valve. And it's nice because they call it a swing, and that's exactly what it does. It flips open when there's water pressure that's greater on the inlet side than the outlet side. And then we'll talk a little bit later about how that gets used and why it's used. You can also put this in a vertical position that you can't do with everything, but the water is only going to be able to go one direction and check it so the water does not come back into the system or does not drain. So again, we will go through that in a little more detail. Spring check valve. Just like it says, there's a spring in there that's at a certain tautness, and some of them can actually be adjusted to have a bigger check. What a bigger check would be something that could be, let's say you had 10 foot in elevation, but and then you wanted to check the water. So when you shut down the system or the spray head, you could put underneath that particular spray head, if it didn't have a built-in check, you could put one of these guys in. And what that would do is it would stop the water from draining from that head down, into the pipe, into the lower areas. That way you get rid of low head drainage. So that is it's a great feature. So what we're going to do now is I'm actually going to move over to a video. And I won't take credit for this one, except that I did find it. This is about a minute, a little over a minute and a half video. And she will explain, she's a supplier, and she will explain the differences between a swing and a spring check valve. So it's one of the best ones I think I've ever seen on this. Not everybody gets into check valves.
Hey, it's Emily from SupplyHouse.com, and in this video, I'm going to talk about the differences between swing check valves and spring check valves. Check valves are piped in line to ensure the flow direction in water and gas applications to prevent backflow in a piping system. The direction of flow is shown with an arrow on the valve. This is important as the side from which the fluid enters and exits must be correct when installed. The two most commonly found styles of check valves that SupplyHouse.com carries are swing and spring checks. Swing checks have a hinged door shaped like a disc that hangs inside of the valve. Pressure from the fluid entering the inlet pushes the door open, allowing flow to the outlet. The door only opens one way, so fluid pushing from the outlet will not flow backwards through the valve. Swing checks tend to be less expensive and impart low resistance to flow. They can be installed horizontally and vertically, where the fluid flows from the bottom up, but cannot be used where flow travels in from the top to the bottom, as the disc will hang open if there is no flow. They may make noise when closing due to the disc slamming shut when flow stops. While swing check valves rely on gravity to close when there is no flow, the disc on a spring check valve is held closed by the tension of a spring inside the valve. Pressure on the inlet pushes against the disc, overcoming the spring and allowing flow. The disc cannot open when pressure is applied from the wrong direction. Spring checks can be installed in any orientation and provide a greater degree of backflow prevention than a swing check. They tend to be more expensive and may create greater flow resistance, but also tend to be quieter than swing checks. Swing and spring valves come in a variety of materials including brass, bronze, stainless steel, or PVC, and many connection types including press, sweat, pipe threads, or solving connections.
So we should be coming back to this, and I will talk about this. So there's a lot of different types of products that we have that have built-in check valves. To me, check valves are underrated, and they're not always used. We have this particular one I'm showing you, just the overall spray head, which you all know. You at least know the 1800. This is the rugged and durable 1800. But in the base of this, at the base of the stem, you'll see down here, and I'll give you a close-up in a second, this is called a seal-o-matic check valve. So seal-o-matic was a term that Rainbird coined quite some time ago, and it's also called or referred to as a SAM for seal-o-matic. Now, if you want to get just a little bit closer view, so what happens is when the system is turned off and the spray head and the riser comes down on the base here, see where the arrow is, this will actually seal right on top of here, so you will not have drainage. Now, in this case, with the RD 1800 or our 1800 spray head, spray bodies, the seal-o-matic check valve holds back 14 feet of water. So what that means is if you had at the bottom of a slope, which would be at 0 feet elevation, and you went up 14 feet, any heads that were placed within that range from 0 to 14 feet, if they're all in the same system and they have a check valve, there will be no low head drainage, which means you'll save water, you'll water more consistently, and you won't get erosion, which is a liability. Actually, it's a big liability. Most of you that I know of have already been specifying this for years, but I'm showing you this so you can see this, so we have it in a lot of different products and the way it actually works. Now, the check valves, you have to pay attention. They have different checks. They're usually not the same, probably for engineering reasons, I would think more than anything. And we're always working to increase check valves where appropriate. Now, the thing is, check valves also can affect pressure loss a little bit. So we don't want to have like a 20-foot check, because when you have that, you have more pressure loss, which means you're going to have more pressure for your system. Of course, that's great for us if you want to spec a pump, but in a lot of cases, you do not want to pump, or maybe a city doesn't want to add a pump and they would rather not have something like a 20-foot check. In other words, that's why we don't even offer that. But a 7-foot check is a good check valve. Now, when you get into our larger rotors, if you're using rotors and you're doing parks and that type of project, we have the 6500, which is about a 65-foot throw with a 10-foot check, and then the 8000 series, which is a 10-foot check, and that throws about 80 feet. Now, in drip, check valves are a little bit different. There's a lot of misunderstanding on drip line. I get the questions, I don't know, probably from 10 or 20% of my specifiers throughout the years. They'll say, well, they normally don't see the check valve or the actual emitter inside the drip line, but there is a check valve. It's actually on the left side of that copper chip inside that clear plastic tubing. Well, since most of them are solid colored dripper line, you don't see that. So they think that the check valve is actually every 10 feet or every 20 feet within the drip line itself. And I'll talk to you a little bit about the advantages of that. I thought you might want to see the inside. I took these photos a little while ago, and about the inside of an XFS-CV emitter that holds back 10 feet. Now, that holds back more water than anybody in the industry. So check valves are important. I don't care what manufacturer you use, but actually I do care, you know that. But as far as check valves go, you see that little dome? We have a dome that's unique to Rainbird, and that particular dome holds back 10 feet of water. Now, I did have like a 3-minute video on how that works, but if you want a link to that, I can give it to you later. It's not that incredibly interesting, but some like to know, engineering types, I think, like to know how that actually works. Then you look below, and it just shows, gives you an idea of a slope area, and you see the blue just indicates for water, and then you've got the brown line, which indicates to be the XFSCV drip line. Now you can see this is parallel to the slope or to the contours. You could put it vertically also up to the 10 feet, and you wouldn't get any drainage or low emitter drainage out of any of the emitters in the system. So it's, this is a good graphic of the way that this would work on a slope. So let me get to the next. Now, we don't always see slopes like this. This is a project I worked on before, and it's an 80-foot vertical slope. Now that 80 feet is actually not the whole way down on this picture. It's up here from this point. You can see the drip line all the way up to here. And as you know, most slopes are 2 to 1, 2 feet to 1 feet, but this is almost a 1 to 1, really hard to navigate and everything else. But it's even more difficult to irrigate this. So this was going to be planted with Rosmarinus as a fuel mod type of planting. And then get you a little closer look. Now you get an idea to see, and like it says here, when do you use a check valve? Well, what happens if the vertical slope, which in this case is more than 10 feet? You actually have to put secondary check valves, which would be, in this case, we used a swing check instead of a spring check. So the water on this, the valves have to pump the water or push the water up. And then when the system shut down, it stops. Sort of like a backflow prevention device. It has a very similar function, except this is critical so you don't have low emitter drainage, because each emitter inside that drip line is only holding back 10 feet of water. So anything that's more than the 10, you need to have a secondary check valve, whether it be a spring check or a swing check. You can see how steep this is, but you can also see how successful and even the planting is. What you have to remember is when you have a check valve, you can do very consistent watering, because every emitter goes on and off at the exact same time, whether it's a flat area or a sloped area. Also, you can, if you time it right, you can actually keep this from doing any erosion or very little erosion on a slope, which is super important. Again, for liability, you don't want your project sliding down the hill, which does happen every so often, and irrigation can be the culprit if not designed right. So I would say there'd be absolutely no reason not to do a check valve in this case or this scenario. So some details. We have all these details online. I just wanted to point out a couple quick things without going through all of it. But this would be a detail for, let's say, a 30-foot high slope. And you can see the blue arrows on here. The blue arrows indicate where either a spring check or a swing check would be placed. Okay, so this particular one, the valve's up here. You could have the valve, this is the TOA slope, and up here would be the top slope. So this is if you do a one valve configuration. So with one valve, it's going to be less expensive than doing 2 or 3 valves, but you have to put multiple check valves to check that water. Anything, again, above the 10 feet, you're going to have to put an additional check valve. So when we go to the next one, and that's not my preference, honestly, it's not about selling definitely more product. It's about liability and efficiency. Because what you have to think about, that each one of these lines, if you have the check valve and you do this correctly, you can really manage the water. So if you have 2 valves, you can even do a better job, because you're able to manage the bottom third of the slope on one valve and the top 2/3 of the slope on another valve. So my example would be like on the TOA slope or toward the base of the slope, you're going to end up having, if I had a question. Okay, we're good. Sorry. So on the base of the slope, what's going to end up happening is if you don't do this correctly, you can't adjust this. Like for instance, the base, you always get more water. And that's with rain, with moisture of any kind. But if you have this on a separate zone, we could put maybe, let's say 15 minutes up here, and down here we could put 5. Or we could do different days. So we have more options with 2 valves. And we only have to use 1 check valve. That's it. Now, to me, this is the, by far, best solution. Granted, it takes another valve. But with 3 valves, this gives your contractor and yourself the maximum flexibility on irrigating a slope. Because, 1, you don't need to have any additional equipment as far as check valves go, because all these irrigate 10 feet. So there's 10 feet at the top third, 10 feet at the middle third, and 10 feet at the lower third. So I literally could program my controller to make these all the same, or most likely make this have the least amount of water, medium, and the most. So this, to me, you have the maximum control. You do all the same flow rates. You'll see everybody doing these differently. They've been designed by multiple manufacturers different ways for years. This is truly the best way to do this, to reduce your liability and also your plants. Sometimes we forget about that part of it, that if they're getting too much water down here and this was all on 1 valve, this is going to get too much always, and this will not get enough. So you'll never be able to balance your water correctly, where if you do the 3 valve scenario, you will. So when do you use a check valve? I'm still asking the same question. Subsurface, sloped, or on surface. Any one of those 3, you should be using a check valve. And there's some reasons behind that. Nobody tends to argue about or challenge the whole check valve situation with slopes, but on surface they're like, well, Mark, I have a level area. I don't need a check valve. There's not going to be any drainage. That's a good argument, except the reality is there is going to be drainage. Every time you turn the system on and off, it will drain if you don't have a check valve. And no areas are completely flat. We all know we need at least a couple percent to 5% grade just to push the water for drainage away from your house or your building or whatever it is you have. So it has to drain. But when this drains out, what's going to happen? You're going to get air in your drip line. Then when the system comes back on, you're going to have to push water back into that system, and you're going to get different amounts of water coming out all these emitters. So even though the emitters are putting out 0.6 or 0.9 gallons per hour, you're going to have varying amounts. So the emitter's doing what it's supposed to do, but because it is a non-check valve product. So even on ours, we make non-check valve products, but in most cases, unless you have major pressure issues or something like that, you should always do a check valve. And then look over here, subsurface, same way. You still want to use a check. This is a drip line live demonstration. Unfortunately, I can't do this right in front of you today, but I can send a video that I put together that shows a lot of, call it a drip line pyramid. What this does is this actually has, and it'll be a quick little video that shows you the difference. What happens when you have, like on the right side here, you'll see there's the copper, which is our XFSCV. This has a check valve and all the emitters. There's 3 emitters in each row. And then there's a cup under each one of the emitters in the middle, so you can get a rough measure of, actually it's pretty accurate measure of what's actually happening. And then the other side, it's a non-check. So let's see, I'm going to switch this over to the video, and we can take a look and see how this works. This is our triangular slope drip line display. What
we're going to do is do a comparison between the XFSCV with the check valve and copper to the XFD or any product that's a non-check valve product. So we'll go ahead and turn on the system. Now, our operation indicator stick shows that we have at least 20 PSI, which will run all these filters. And again, this is the check valve, the XFSCV. It will check water up to 10 feet in height, which means every emitter will go off at the same time when the system depressurizes and turns off. We look at the XFD side. This side does not have a check valve and will continue to drain until the water is completely out of the dripper line. So what I'll do is I will turn this off. And again, this is a fairly short demo. You'll see right now everything continues to run. They're all at 0.6 gallon per hour emitter. And there's 3 per drip line on each elevation. The operation indicator stick, it shows there's still pressure in the line at probably about 20 PSI. So until that lowers, things will continue to run or the pressure reduces. We'll take a look at the check valve side. We'll already see that the emitters are shutting off. In fact, all of them at the same time. And it'll be the same amount of water in every cup. So we'll go to the other side now that the operation indicator stick has completely gone down, and we'll see that on the top the water's pretty much stopped. On the middle row you'll see it's still running, and then on the base it's running also. Each cup, after a period of 10 to 20 minutes, will have a different amount of water, the least amount on the top row and the most on the base. And you can already see, even though these have the same flow rate, each dripper line, you can see that the non-check valve versus the check valve are different amounts of water. So what are the advantages here? One, with XFSCV, a check valve product, you do not have low emitter drainage, which promotes better and more consistent plant growth and deters erosion. Where on the non-check valve side, it continues to drain, which means inconsistent watering and more water at the base and toe of the slope. Again, this is our triangular slope drip line display.
Okay, so that gave a pretty good example of, if you can see on there how that worked, but I wanted to make this a little bit more measurable, because I think one of the things that end up happening is like, okay, well, overall you're going to save some water because you have a check valve, but really how much is that on a slope situation, even if it's a couple feet? Well, I went through there, and this is, again, this is unofficial. This was not done by Rainbird or anything like that, but I don't think we really had any information like this. So I decided, you know what, I'll just make my own, and then we'll just make it work. And I've done this several hundred times before I made this video, and then I went ahead and collected some data. So this is what I came up with. There's about 10 ounces wasted per cup per runtime. Give you an idea, okay? If there's about 1,000, let's assume we have 1,000 emitters, which means there'd be one emitter every 12 inches for 1,000 feet, or it could be 1,000 square feet of area, which could be like a 10-foot wide by 100-foot long area. I want to give an idea of how much water, again, is wasted, not just the 10 ounces. So there's about 10,000 ounces, not gallons, 10,000 ounces wasted per runtime for that length, which equals 78 gallons wasted per each runtime. So every time the system comes on and off, you waste 78 gallons of water. Now, some on slopes will water cycle and soak. So they'll turn it on for a while, turn it off for a while, turn it on for a while. They'll do that all in one day and divide it up. If you're doing that and you have a non-check valve product, you will waste even more water. So let's say, make another assumption that there's only one runtime that you're going to do a week, 52 times a year. That's not, that many times. Most will run their system more than that, but I thought I'll keep it at a low number. So total, you're looking at a waste for 1,000-foot line of emitters of a non-check valve and a sloped situation, 4,000 gallons of water wasted. And that's just for one zone. So if you had 10 zones or 10 stations or 10 valves worth of drip, you're talking 40,000 gallons of water. Now, granted, it's not a ton of water, but just because of whether you made a selection to do a check valve versus a non-check valve, and also picking up erosion and all the other issues, the inconsistent watering that you'll do, this will solve a lot of that for you. And this, again, also applies to sprays, rotors, rotary nozzles, anything like that. Everything should have a check valve. Okay, one last one. The RWS, which is our root watering system, these can be specified with check valves in them. And again, if you look at even money-wise, it's not a lot of extra money for what it does. The check valve holds back 14 feet of water. And what that looks like is like this. So inside, we have a check valve. So if you look at the right-hand side of this slide, it's sort of a gray color. This is actually a spring check that holds back 14 feet of water, which is huge, because when you have these guys on each side of the tree and you just had a long median or something, when it drains down, this water at the base of the slope, and it's not much of a slope, just could be a center median. So anyway, that would be a good